Okay. So in the last class, we are done with the electronic configuration of the elements. So I'm just going to discuss the electronic configuration for the cation and anions, and then the orbital filling thing that we will discuss quickly, and then move to the ionization energy. Okay. So what happens in cations that they have a lesser electrons, right? Okay. So we are going to remove their electrons from the valence shell. And the anions usually have more electrons. So we are going to complete the outermost subshell. That's what we do. Okay. The next thing, there is a little complication or little change in the when you are writing the electronic configuration for the cations of transition elements. Okay, so let's discuss over here. For example, if I talk about sodium, so sodium is 1s2, 2s2, 2p6, and 3s1, right? So when I move to its uh, ion, at this ion, its ion has a +1 charge, which means it has a one less electron. So you are going to write it 1s 2s2, 2p6, and then either you write just 3 as 0, or otherwise, if you don't write that shell from which subshell from which the electron is released, either way it works. Similarly, for example, if you look at aluminium, it is 1s2, 2s2, 2p6, 3s2, 3p1. So as its sign got 3+ charge, so it means the electron are going to be loose from 3p and 3s both. So yeah, the electronic configuration is going to be 1s2. Yeah, it's up to you. You can do both the ways. Assalamu alaikum Arham.
Assalamualaikum, sir.
Walaikum assalam. So we are going to write 1s2, 2s2, 2p6 as it's a 3 positive charge. So it means 3 electrons are actually get lost. So it is going to be just 2p6, or otherwise if you mention the rest of the two, so you can write it 3s0 and 3p1 in, oh yeah, 3p0. So both way would be fine, 3s0 and 3p0, or otherwise you don't write them. Okay. Now for the transition elements, okay, what we really do for the rest of the cases, we move in one order, and the subshell which we filled in the last, when the atom becomes ion, that the electron are going to be lost from that subshell only. But in the transition elements, what we do, we usually fill the 4s first, and then we will fill the 3d. So when we are going to remove the electron, we are going to remove the electron from 4s first, and then we are going to remove from the 3d. Okay, so let's have a look at the example of iron. Okay, so iron has 26 electrons, right? So as an atom, its electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then 3d6. So the thing is that that's what I have discussed in the last class as well, that when you see the marking scheme, so in marking scheme, it is actually like this: 3s2, 3p6, then it's 3d and 4s. So remember, if you write this way, you are going to fill the 4s first, and then you are going to fill the 3d. So it's better to write 4s and then 3d. Both are considered as correct. Okay. So it's better to write 4s because you are going to fill the electrons in 4s first. So for example, if you write 3d before, and you by chance forget and you fill the rest of the electrons in, yeah, it can be 3d8. तो आपको तो लगेगा कि you find that it's right, but actually it is going to be wrong. So it's better to write 4s first and then 3d6. Okay. So the next thing that I told you, yeah, for all of the transition elements, we write 4s. It's better to write 4s first and then 3d and fill the 4s first and then the 3d. Is this clear? Okay. Next, it has two positive. So if it is two positive, so it means it is going to lose two electrons. So remember, those two electrons are going to be lost from 4s. So the electronic configuration would be like this: 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. And over here, if it's a 3 positive, so it means that the first two electrons are going to be lost from the 4s, and then the third one is going to be lost from 3d. So the electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, 3d5. Because, yeah, sorry, 3p5, 3p6, and 3d5. Yes, is this clear? Okay, so for anions, we fill the electrons in the outermost subshell, so it becomes completely filled. For example, if I take the example of nitrogen, and when it turns into nitride ion, it has a three negative charge. So if I write the electronic configuration of nitrogen, it is going to be 1s2, 2s2, and 2p3. So see, it is a three negative charge. So it means that the three electrons which is gained is going to be gets filled in 2p only. Yeah, the outermost subshell. There is no more subshell which would increase. So that is the important thing. So it is going to be 2p6. Okay. So similarly, for example, if I take the
Sir,
example,
is this iron nitrite or nitrate?
no, it is nitride. Okay, let me clear this thing. Just give me a minute. There are three ways we actually name the anions. Okay. So for example, if I have a sulfur, it's 16. So its electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p4. So when it turns into an anion, it gain actually two electrons. So yeah, the 3p4 would turns into 3p6. So 1s2, 2s2, 2p6, 3s2, and 3p6. Okay. So the thing is that, for example, if you are going to name any cation, it's really simple that you are going to write the name of element and then you will write ion. That is the way you always name the cation. For example, if you have a sodium +1, so what you are going to name it? Sodium ion. If you have a aluminium +3, what you are going to name it? Aluminium ion, right? So for example, if it's a Na plus, so I'm going to call it sodium ion. If I have Al3 positive, it is going to be aluminium ion. For example, if I have a Fe2 positive, I'm going to call it iron 2 ion. because it's a transition element. So with the transition element, we always write the name in the Roman. Is this clear? Okay. So then the name of anion. So the thing is that in anions, the suffix of the name gets changed. So there are 3 suffixes. Okay. So suffix is not same as the name of element. Ram, are you a regular student or a private student?
So I'm not private.
Okay. So in which college you are?
Next year.
Mixer. Okay. So there are 3 suffixes. One type of anions have ID in their name. Then one others have ITE and ATE. Okay. So it means, for example, if it's Cl negative, Br negative, I negative, F negative, what we are going to call them? No, yes, no. So now they are not chlorine, bromine, iodine, and fluorine. They are going to be named as chloride, bromide, iodide, fluoride. Okay. Is this clear? Okay. So similarly, we have just discussed N3 minus and you have asked what it is called. So N3 minus, so it means it is called as nitride ID. Okay. So, but if nitrogen is bonded to 2 oxygens and forming a ion with the -1 charge, so it is called nitride ID. And if it's NO3 with the -1 charge, then it is called nitrate. Is this clear? Then sulfur with a 2- charge, sulfide, sulfur with SO3 with the 2- charge, sulfide, and sulfur SO4 with the 2- charge, sulfate. Similar. It's ID, but there is one exception in this as well. But beside that, if the single atom is there with the negative ion, then it is ID. Otherwise, if it is bonded with the oxygen and forming an anion, then it is either ITE or ATE. Yeah. So it is going to be phosphide, then PO3, 3-, and PO4, phosphite and phosphate. Is this clear? Okay. Now, beside this, OH-. So see, this is only one exception where there are 2 elements and it is all still called hydroxide ID. Okay. Then we have a CO3 2 negative and HCO3 2 negative. So one is carbonate and the other one is hydrogen carbonate. Okay. Then we have MnO4 negative. So what would it call? Manganate. And we have one more, Cr2O72 negative. What one this one is called? Dichromate, because there are 2 chromium. So the important thing is this. See, when you look in the periodic table, you will find these in group 7. So it means they are going to gain 1 electron. So from the periodic table, you are able to recall that they are going to form an ion with the -1 charge. Similarly, it's in group 5. So it is going to gain 3 electrons. So it is going to form an ion with the -3 charge. Same with the phosphorus and sulfur is in group 6, like oxygen is in group 6 as well. So they are going to gain a -2 charge. But this is really important that these polyatomic ions, which I am highlighting right now, you guys need to remember them, their name, their formula, and their charge, because periodic table is not going to help you with these. For example, if magnesium carbonate is written, so magnesium, you will look in the periodic table, you will find it's in group 2, so it's a +2 charge. But carbonate, you are not going to find carbonate anywhere in the periodic table. So you must remember, when it's carbonate, your mind just click that it is CO3 with the 2- charge. So that's what you need to know, and that's what you need to remember. So these, the highlighted ones are that must be remembered. That must be on your fingertips. Is this clear? Any confusion so far? Yes, Mariam, did you understand this?
Yes.
Yes, Arnam?
Yes, sir.
Okay. So in the last class, we just go over the electronic configuration of cations and anions. In the last class, we have ended over here. We discussed these two exceptions, and we have discussed that they become stable because one electron gets jumped from 4s to 3d in both the cases, and that makes them more stable. But the thing is that how these able to jump? Usually that won't happen in the rest of the cases, but they only happen over here. So what is the reason? So I'm going to just discuss the two reasons. One reason is about this, that why they easily jump into the other from 4s to 3d. And the other reason is about why the electrons are actually getting removed from 4s, but not in 3d, not from 3d. So this is the case. For example, when the atom is empty and the electrons are being filled. So first thing, if you see that the energy gap between the subshells are high, but between these two, the energy gap is very small. So it's become easy for an electron to jump from 4s to 3d. So that makes it easy. And the other thing, you see the energy of 4s is at a lower energy, and 3d is at a higher energy. Okay, so that's why after when the 3p, what happens that the 3p gets 6 electrons, and after these electrons, we are getting the next electrons in the 4s, and then it's turned for 3d, right? So, but as soon as the electrons get filled in 4s and 3d, it would actually turns their positions. So 4s have a now higher energy than the 3d, and that's why when we provide an atom energy to make it a cation, its electron gets out from 4s first and then 3d. Is this clear? Okay. Now, the next thing is orbital filling. I hope you all have done the orbital fillings. Yes, Mariam, are you done with the orbital filling, right?
Yeah.
Arham, do you know how we do the orbital fillings?
Yes, sir.
Okay. So, uh, for example, let me take the example of nitrogen. Nitrogen has 7 electrons. So its electronic configuration is going to be 1s2, 2s2, and 2p3, right? What we know that in 1s, how many orbitals it have? One orbital. And in 2s, how many orbitals? One. And in 2p, how many orbitals? Three orbitals. So when I'm going to fill the electrons in 1s, what I do, I put one electron like this, and I put the other electron like this. Okay. So it means this is the pair of electron, right? So what is the charge on electrons? Negative, right? So my question is, if the electrons have a negative charge, then how do they get paired? Isn't it they must be repelling each other, right? If we all know, yeah, that if there is opposite charges, they attract each other, and if there are same charges, they repel each other. So we know that both are electrons, so both have a negative charge. So how they get paired? Yes, Arham, do you know the answer?
Sir, they get attracted to the other like the other atom's nucleus because it has protons.
Yeah, they get, yeah, you can say that, but how could that makes them to be in pair? And you're talking about when the bond is being formed and afterward the molecules are formed. So the molecules, the other atoms molecule can attract. So this is that is the very different case. But I now think of our isolated nitrogen atom. So we know that in isolated nitrogen atom, the electronic configuration is like this, that 1s has a 2 electron and 2s has a 2 electron and 2p has a 3 electron. So if 1s is only one orbital, it is a one space where the 2 electrons are just paired. So if they both are negative charge, so how do they get paired? Yes, Nile. Okay. Yes, Mariam, any other reason?
I'm not sure.
Okay. Yes, Arham, do you know, or do you just guess any reason?
I thought that's what Mariam said.
Okay. So the thing is that, what do you know about the movement of electrons? You all know that electron is present outside the nucleus. So how electron is actually moving, or electron
They're
is,
spinning around the axis of the shells.
it is spinning around the axis, or it is spinning around the nucleus?
Yeah.
So actually the thing is that electron has two movements like our earth do. Our earth, Mariam just said that it is spinning on its own axis, and it is revolving around the nucleus. Like if we talk about our earth, what our earth do, that it is orbiting on its own axis. That's why every 24 hours that we got the sun and the moon, and beside this, it is moving around the sun as well and completing that whole circuit in distance in 365 days, right? So the thing is this, that electron has two movements. One is that you know since your junior classes that it is orbiting around the nucleus. And the second movement is that it is orbiting on its own axis as well. So see, if you look at this electron, for example, so electron is not just moving around the nucleus. Beside this movement, it is moving, or it is spinning like this as well. Is this understandable? Okay. So the spin of electron can be of two types. one type of electrons are actually spinning in a clockwise direction, and the other type of electron are spinning in the anti-clockwise direction. So what happens, they do have a negative charge, but their opposite spin actually minimize the repulsion of the same charge. And that minimization of the repulsion makes them to come closer and become a pair. And see the reason, if you see over here, when you put two electrons in one orbital, you show one electron moving upward and one electron moving downward, right? You don't pair the two electrons like this, or you don't pair the two electrons like this. So this is what it indicates, that if this electron which is on the left has a clockwise spin, so the electron on the right has a anti-clockwise spin, or the opposite way. So these directions are indicating that they have a opposite spin, and due to that opposite spin, these electrons, the repulsion between them is minimized. So remember, I'm again using the term and emphasizing what, that the repulsion is minimized. It doesn't mean that now there is no repulsion. There is repulsion, but that repulsion is now very low, and that's why they become a pair. Is this clear? Yes, Mariam, did you understand this?
Yeah, I did.
Okay. Yes, Arham, did you understand this?
Yes, sir.
Okay. So that's why whenever we make the pair like this. One electron having a upward arrow and the other electron having a downward arrow. And when, if there are two electrons having a same direction arrow, it means they both have a same spin. So if they want to be a pair, they become, so what they will do, one of the electron would change its spin, and then they would get paired up. Is this clear? Okay. So that's what I think Mariam did it. And so in the next class, I'm going to check these orbital filling for the first 30 elements from hydrogen till zinc. Okay. And Ram, I hope you can do it easily.
Yes, sir.
So this way we do the orbital filling. So your task is, that is the home task, that we, in the next class, you make sure that you are done with the orbital filling of the first 30 elements from hydrogen till zinc. Okay. Did you understand?
Yes, sir.
Okay, great. So okay, so when you guys look at the periodic table, you would find the structure is like this. There are two boxes over here, the group 1 and group 2. And then over here, we have a one rectangular box which also contains elements, and we consider them transition elements, right? And then there is one more block on the left, sorry, on the right. It is like this. Is there any other block as well in the periodic table? Yeah, there are two more rows in the, okay, we have one element over here and one element over here, and we have two blocks over here as well. So do you guys know why these are different from each other and why these are arranged like these? Hmm. 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 And after the staircase, we have the non-metals, right? So the thing is this, I'm talking about these boxes. So yeah, the top one is a hydrogen and the extreme right is the helium. So the thing is that this box, which is on the extreme right, these two groups, these are called, or this block is called S block, or this is called, we call it S block elements. Similarly, this one is called P block elements, and this one is called D block elements, and this is F block. So why is it so? Very good. So the thing is that the last subshell, if the valence subshell is S, then those all elements are over here. Those elements whose last subshell is P, then those elements are over here. And those which have a last subshell is D, then those elements are in this region. And the elements which have the last subshell is F, then these are in this region. Is this clear? Yep. Yes, Arham and Mariam, did you guys understand this?
Yes.
Yes, sir.
Okay. So if we further look into periodic table or in these blocks deeper, it is, we have a further more precise arrangement as well. See, what we know that these are the periods, right? These are the periods. So if I have any element over here, so I'm able to predict that its elements is electronic configuration is going to end at 6s2. And if I have this element, so its elements electronic configuration is going to be 4s1. If I have this element, so its electronic configuration is going to be end at 7s1. So how could we know that, as we have just decided that these two are the S block, right? So the first group, all of these elements are going to be end at 4s1, and their period gives you the shell in which it is. So it is going to be whether 5s1, 6s1. So by looking at it, you are able to identify the last electron where it is located. Similarly, all the elements which are in group 2, they are going to be have a S2. For example, if you guys have a periodic table, let me open it over here. Here we go. So see, it is calcium, right? Calcium. So calcium is in group 2, and in its which row 1, 2, 3, 4th. So it means its electronic configuration is going to be end at 4s2. So you can check over here. You guys did the electronic configuration in the last class. So similarly, when we move over here, so all the elements which are in group 13, they are going to end at 4p1. They are going to end at p2, p3, p4, p5, and p6. So for example, if I take this one, so from here, I got to know that its electrons, the outermost subshell is going to be p, and it has a 4 electrons. And if I count the rows, 1, 2, 3, 4, 5, so it is going to be 5p4. Is this clear? Yes, Arham and Maria?
Yes, sir. Yes, sir.
Yep.
For the D, there is a little complication over here, and that complication is it's actually like this. It's a fourth period, right? So all of them are going to be start from 4s, but the D is always going to be the previous shell. Yeah, the S is from the fourth shell and the D subshell is going to be from the previous shell. See, if you recall, we first filling the 4s and then we were filling the 3D. So 3D means 3 is from the previous shell, right? So similarly, so see, it is going to be 4s2 3D1, 4s2 3D3, 4s2 3D2, 3D3, and then here we got the exception 4s1 3D5, then 4s2 3D5, 4s2 3D6, 4s2 3D7, 4s2 3D8, 4s1 3D10, which is exception, which is copper over here, and over here it's a chromium, then 4s2 3D10. So see, if you got this, then for example, if I look over here, so I can predict its configuration as well, where it is going to be end. So if it's fourth row, then it is going to be fifth row and it is going to be, so it is going to be 6s2 and 5d7. And if I look at over here, so it is going to be 7s2 and 6d5. If I look this one, so it is going to be 5s1 and 3d5. If I look at, yeah, 4d5, sorry. And if I'm going to look at this one, so it is going to be 6s1 and 5d10. So that's how there is no need to write the whole configuration, but you are going able to predict or able to identify the
Sir, I didn't get it. Could you repeat it again?
Which one?
The whole D block, how we use the previous number.
Okay, you got these number, right?
Yes.
Okay, so it's fourth row. So in a fourth row, the S is from 4 shell, but the D is always from the previous shell. So that's why it is 3D. Is this clear?
Yes.
Okay. So for example, if this is chromium, this one is chromium, its electronic configuration is ending at 4s1 3d5. So the one which is below it is going to be end at like 5s1 4d5, and then the one which is below it is going to be 6s1 75, and the below one is going, oh sorry, not 75d, and then 7s1 and 6d5. Yes, and the D usse ek period, the one period which is before it, which is above it. We take the D from that one, and the S is from the same period in which it is. Yes, now did you understand, Mariam?
Yes.
Okay, what about you, Arham?
Yes, sir.
Okay. So the next thing that we are actually moving on is ionization energy. Okay, so what does I'm just talking about ionization. So what does ionization means?
An element gaining or losing electrons.
Very good. An element
So
gain
turning into an ion.
electron to become an ion, that is what ionization. Okay, so when we talk about ionization energy, so yeah, so the initial concept we got that the energy that is needed to make an element, an atom, an ion, then turn into ion. So the first thing that you need to remember is that this energy is always specific to the formation of cation. That is really important. And that's why I ask you, what does ionization mean? So whenever you guys have heard or listened the word ionization, it always come in the mind that it's the formation of ion. Yeah, ionization means that the formation of ion. And both cations and anions formed. But whenever we use the term ionization energy, so this energy is always associated specifically to the cations. Is this clear? Yeah, it is nothing to do with the anions. Okay. So what energy it is? You can say that it is the energy change when cation is formed. Is this clear? Okay. Yes, Arham, can you give me any example of any element?
Chromium.
Chromium. Very good. So which kind of element it is? It is a metal or a non-metal?
Non-metal, sir. No, metal.
Metal. So what would be its state? It's going to be a
Solid.
room temperature, right?
Yes,
So
sir.
the thing is, if first thing, can I able to knock electron from this chromium atom or not? Can I able to remove?
Yes, sir.
How?
Ionization energy required अगर वो reach हो जाती है.
Okay. So how would the ionization energy reach over here? So the thing, it means you are telling me that we need to provide the energy to it, right? And we are
Yes,
going to
sir.
provide the energy until it removes the electron and turn into ion, right?
Yes, sir.
Okay. So now, when you provide the energy, how we usually provide the energy? By heating something, right?
Yes, sir.
So if I
Applying heat.
heat it, what is going to happen to it? First, yes, then it's if it's going to change its state, right? So when you heat some solid, what is going to happen? It is going to turn into a liquid, right? Yes, sir.
Yes, sir.
Okay. So if I continues to heat, so finally, if its melting point is reached, it is finally turned into a gas. And when something turns into a gas, what happens between its particle? Now there is either no force of attraction or there is a negligible force of attraction. So all the atoms gets isolated from each other, right?
Yes.
Yeah. So now there is a single atom. Now, if we further provide the energy, then it is going to lose the electron and turn into a cation. So that energy is going to be considered as ionization energy. If you provide the energy and turn it into this, so that energy is not considered as ionization energy, because over there, not just ionization, not just the cation formation is taking place, but before that, the energy is being used up to turn the solid into liquids. Then further, the energy is used up to turn the liquid into a gas. And when it turns in, finally, it becomes a gas. Now, if I further provide the energy, now the atom is vulnerable, it's exposed, its electrons are clearly exposed. So now the electron is going to be get out from it, and that energy is going to be considered as ionization energy. Is this understandable?
Yes, sir.
Yes, Mariam, did you understand this?
Yes, I did.
So the important thing is that to form a cation, the element must be in its gaseous state. Then we are able to measure that energy and we can name it the ionization energy. So, and okay, now the next question, how do we remove the electron? So we use an instrument or device and we call it spectrometer. To remove electron, spectrometer is used. And the next important thing, chlorine is a non-metal, oxygen is a non-metal. When they react, what they do, they gain electron. But with the spectrometer, we are able to turn any element into a cation. So it means that the ionization energy is not just associated with the metals, it is also associated with the non-metals and actually those elements as well, which you usually observe as forming an anion only. We can remove the electron from those and we can turn into cations. Walaikum assalam, Allah ka shukr. Okay, okay. Is this understandable? Okay. So that is another important key point for this, that any element can turn into cation by spectrometer. Okay. Now, if I am able to remove one electron from one gaseous atom, and as we have discussed, when the electron is being removed from the gaseous atom, then that energy is called ionization energy. But do you think if I have just a one atom in the gaseous state and I just able to take the electron from that atom and I have calculated that energy. So do you think that energy is actually a significant energy? Or that energy have a high value? Why? It's just a single one atom. Yeah, but for example, if you have a small sample of a sugar, like 1 spoon, and you have a like one huge tank of a sugar. So are you going to provide the same energy to melt them? You are going to heat them, but obviously the sugar which is in 1 spoon is going to melt it very quickly, right? And similarly, when the whole that tank is going to be, if I need to melt that whole tank of the sugar, it needs a lot of more energy. So that's what it is, that we usually, when we do these kind of things, we have just discussed, that the atom is turning into ion and the energy needed to make the atom into a positive ion, that energy is ionization energy. But when that I have explained you, but when we are going to state these things, we always consider 1 mole to make the things standard and comparable. So if I'm going to define the ionization energy, I'm going to define it in terms of 1 mole of atoms. And if I am saying 1 mole of atoms, then it means how many atoms there are? 6.02 exponent 23 atoms. So yes, when there are this much atom and each atom is going to lose one electron, so the amount of energy that is being used is now significant and it is now a higher value, which matters actually. Is this clear? Yes, Mariam, is this clear to you as well?
Yep.
And yes, what about you, Arham? Did you understand?
Yes, sir.
Okay. So the definition is really important. Okay. So examiner asks you the definition for the 2 marks or the 3 marks, and examiner write it like this, that define the first ionization energy or the define the drum ionization energy. So either way, you are going to write the definition for the first ionization energy, and it is stated as the energy needed, or instead of energy needed, you can say energy change to remove 1 mole of electrons from 1 mole of gaseous atom. So we have a 1 mole of gaseous atoms, and we provide enough energy that each atom from that 1 mole loses 1 electron. So in total, 1 mole of electrons get lost, and we get 1 mole of gaseous 1 plus ion. Is this clear? So here you have a definition, and then you can represent the chemical equation of this ionization energy, and that is the format for chemical equation. Whenever you are going to write the ionization energy equation for the first ionization energy specifically, you are going to write 1 mole of a gaseous atoms of that element on the left side of the equation, on the left side of the arrow, and on the right side of the arrow you are going to put the 1 mole of +1 charge ion only, and 1 mole of electrons being there. So for example, if I need to write the first ionization energy equation for the chlorine, so it would be like this. I'm going to write the chlorine in the gaseous state, and then arrow, and then Cl+1 in the gaseous state, and then electron. Similarly, I need to write the first ionization energy equation for oxygen. So I'm going to put a O in a gaseous state, then O with the +1 charge in a gaseous state, and then the electron. Similarly, for any metal like iron. So iron is also should be in a gaseous state. So that's what the key points we have discussed. Whenever we are going to write the for ionization, the element, the atom must be in the gaseous state, and it can be for any element. So you haven't seen earlier that the oxygen being a positive charge and the chlorine being a positive charge. But in spectrometer, we meet the non-metals positive ion as well, but naturally they don't do. Naturally, they tends to gain the electron and becomes a negative charge. So sometimes students get confused if the examiner write the first ionization energy for the chlorine and they are making the chlorine into Cl minus ion, because that's they in their mind. So yeah, but whenever the ionization energy, it's really important that nothing but the positive ion. So for iron, I'm going to write it Fe plus and then 1 electron. And these all are because we are removing the electron. So electron is being attracted by the nucleus. So there is a attractive forces between the nucleus and the electron, and we need to overcome those forces. So it is, and we are providing the energy. So the ionization energy is always endothermic. The electron gain that much energy. Now it is it have a more energy than the nuclear attractive forces, so it can easily break those forces and come out of the atom. Is this clear? Yes, Arham and Mariam.
Yes, sir.
Okay, so we are keeping the class till here for today, and in the next class we will be continuing from here onwards. Okay.
Okay, sir.
Okay, take care. Allah Hafiz.
Allah Hafiz.
Nice, man.